Okay, I'm Chris Worrell. I'm a consultant at TWI. And if you don't know anything about TWI, you're about to find out soon.
Hi, I'm Jasmine. I'm the composite section manager at TWI. And I work with Chris. Chris is one of the biggest brain in my section. So most of the things I'm showing is coming from him. So if you have any complicated question, you should go to Chris.
Jasmine.
Okay, let me share my presentation then. I hope you can see it, Chris.
I can see that.
Yeah. Okay, first of all, thank you everyone for joining for us to be able to show what we do at TWI. First, I'll give a little bit of a background, not extreme, not go too much into the details. So TWI is a membership-based organization, and we are a non-profit distributing company. So we do make profit, but whatever the profit we make goes back to the business itself. It doesn't get distributed. Our annual turnover is about 80 million, where we work on R&D in materials joining, structural integrity, NDT, structural health monitoring sort of areas. Currently, we have about 800 employees. Most of them are based in Cambridge, where the headquarters is. And then we also have staff in 4 other branches in the UK and also worldwide as well. So as we are an industrial member-based organization, we have about 700 industrial members who are distributed in about 3,500 locations and in actually 800 countries. So we are actually a global organization in that way, I would say. Our offices are in Cambridge, which is the headquarters. And then we also have offices in Rotherham, in Aberdeen, Middlesbrough, and in Port Talbot. And actually, most of the composite works happen in Middlesbrough, Cambridge, and Port Talbot in Wales. What we do is mainly in materials. We call ourselves material engineers. It could be in materials, some part of materials development, process development, in relation to joining, testing and characterization and inspection. So what we do is R&D, research and development and innovation for industry to resolve their issues. And also we provide consultancy in our expertise that we have developed through consultants such as Chris. Then we also have a part where we have a training school and a certification center, which is focusing a lot on the welding side. When I say welding, it's not only metal, it's also composite and polymers as well. And at the moment, this year, actually, we will be celebrating our 75th anniversary. We were going to have a big celebration, but due to COVID, it has been actually postponed to next year. As part of that, actually, I would like to also mention that we will be also having an industrial day for non-metallic materials at TWI. It's mainly focused for members. That was supposed to be held in November, but now that has also been moved to March next year. When we have more details, I'm happy to distribute the information. So as I mentioned, we have offices globally, and they are located in North America, in the South, then in India, China, Australia, and they're widely distributed. It's mainly covering training and technology centers. Most of the R&D work actually takes place in the UK offices. So what we do is we serve our industrial members they actually own us. We don't have different owner for TWI. And in a typical year, we do over 650 single client projects. And then, but in order to support the single client projects, we also need to be up to date with upcoming future technologies. So in order to be up to date with that, what we do is we do collaborative projects to public funded projects such as either Innovate UK or EU or regional funding or ATI or even defense and security accelerator sort of programs. And we do at a time, each year we have about 55 projects or over live. Then the other type of projects we are running is the core research program. So that is funded by TWI, and the way it works is when a member joins, they pay a membership fee, and majority of the membership fee actually been allocated for core research program. And we have a research board which is consisting of selected industrial members, and they decide what projects we should invest in when it comes to core research. And when we do these projects, they are actually available for every industrial member at TWI. Whereas if you take a single client project, that information is only available for that specific client who paid for it. Then another type of project we are running is the joint industrial projects, where we have a number of companies putting money into a pot for a common purpose project, and that results are shared among those members. And then we also sit in different variety of standard committees as well. In terms of industries, I cannot think of an industry we don't cover. We actually work with all the possible industries, as there are a few icons on the screen and you can see. I cannot imagine we are not covering anybody. Are we, Chris? Do you think we are not covering any area?
I don't think so. I don't think so. I'm not sure we do anything in the cosmetics industry, although I could be wrong.
Good
because
point.
There's
but still, most probably we do help with the equipment.
There's equipment and there's materials and there's rheology of these materials. So
exactly. Yeah, so we do nearly cover, I would say, every possible industry. So in general, to place a single client project with TWI, the organization should be a member. In order to work with TWI, without being a member is generally through R&D projects which are public funded, either Innovate UK or Horizon Europe or any other public funded projects is the way to work with TWI if you are not a member. I mean, later on when we go to the Q&A, if you want to ask some question about the membership program, we can provide you some information. So now going to the composites. Before I actually go into composites, one thing I would like to say is that TWI is popular for metals and also welding or joining of metals. That's what they have been popular. Well, it has been 75 years since we have been established. So we are quite popular in that area. And what we are trying to establish, actually, even in composites, we have been working in that area over 30 years. But we are much more known for the joining side. But the advantage we have by working in metals and metals joining is that we provide solutions, not only in composites, not only in metals. We provide a solution that is suitable for the application with the correct material. We do not encourage either metal or composites. We try to identify what is the best way and what's the best material so that we can encourage the correct process. So that's one of the main areas that TWI has the expertise in. When it comes to composites, I am with Chris and my rest of the team. We are leading the composite activities at TWI. However, the composite activities doesn't only take place in my section. Some parts take place in different sections, but we, as a center, coordinate them. For example, the non-destructive testing and structural health monitoring is mainly taking place in Wales. And then we have mechanical testing and also environmental testing, which taking place under another group. But as a whole, what this slide shows is that all the areas we are covering at TWI when it comes to these materials. So sometimes you may directly go to some of these people if you already know them, or you would come to us and we can guide you to who are the best people at TWI in order to support these areas. So I have categorized it to just to keep it simple into 5 different areas. At TWI, when it comes to composites, our main focus is out of autoclave processing of composite. So processing is one of our main themes. And then we have the joining side. Most probably I will ask Chris to talk about it. I didn't warn him, but I'll ask him to talk about it. And then we have the modeling side in terms of process and also performance. And then the structural integrity part is a huge part as well at TWI, where we also do automation when it comes to NDT. And then we do the failure investigation. Under failure investigation, you might be using NDT or mechanical testing or even other thermal characterization methods. And then we do environmental testing mainly for the permeation testing, which we can provide you some information, but we have experts in all these areas. Today I am not an expert. I cover most of the areas, but Chris is an expert in certain area, but we have a number of consultants and fellows who are working in these different areas. But we can give you some sort of flavor of what we do. Then we also have a work on functional composites, where I'll be showing you one of the technologies you may have heard already, SurFlow technology. And we also work on coatings. It can be either metallic coating or a functional coating. So just to start with first, I will go to quickly the processing side. I'm not going a lot into details, but when it comes to processing, one of our main area is the microwave processing of composites. We also work with the hot press, conventional oven, and also RTM, but we don't necessarily do just the manufacturing. What we are looking into either using these processes and on new materials to see what happens to them, or when we also want to do process improvement or process monitoring. One of our main activities when it comes to manufacturing is our expertise in microwave heating of composites. Then, as I mentioned, we do a lot of process monitoring, mainly in understanding the resin flow and also the degree of cure during the processing, where it can be either RTM, it could be even resin infusion, where we assess where the resin flow is so that actually we can alter the resin process, the resin flow. And then when it comes to joining, there are quite a lot. Chris, do you want to say a few words for each one?
Yeah, sure. Have you got one slide on each?
Yeah.
Okay, so there's the 3 different areas that Jasmine highlighted there. One is adhesive bonding, which we'll look at first. Now, we don't formulate adhesives or manufacture adhesives at TW. That's somebody else's business, but we specialize in selecting adhesives for particular applications, so making sure we choose or our members choose the right adhesive for a particular application based on requirements, and also the surface preparation. Getting the right surface preparation technique can be critical for successful application of the adhesive. So one of the areas we're looking at the moment is the plasma treatment, called atmospheric plasma. It's a pre-treatment of both metals and thermoplastic and thermoset composites as a way of not necessarily getting a stronger joint than other joining techniques, but getting equivalent performance in a faster, more efficient and more environmentally friendly process.
Yeah, I think just to add to that, Chris, I think I mentioned about this is about composites, but actually when it comes to adhesives, our section actually leads all adhesive process, whether doesn't despite what the material type is.
Yeah, and also dissimilar materials.
Yeah,
which I think is the third one, but should we look at welding next?
Yeah.
Okay, well, a lot of people are a bit confused when we talk about welding composites, because the idea of somebody with a face mask and a torch welding thermoset composites sounds a bit ridiculous. But actually you can weld thermoplastic composites by the application of heat through a process called fusion bonding. Some people would argue that it's not strictly a welding process, but it's a thermally activated process, and we all understand really what welding is. So there are many, many different techniques available. They're all the same except the way that the heat is generated. So for all the processes you need heat and the application of pressure and time. So the innovations and the variations are all down to how you get the heat in there, how efficient it is, how controllable it is, and what happens afterwards. So for example, how you deal with crystallinity in semi-crystalline polymers. So over the years, going back to when was APC2 first launched in the early 1980s, we've been looking at welding thermoplastic composites and innovating throughout those years. Friction welding. Well, this is interesting because if you try and friction weld polymers, you get very good joints. You just rub them together, it generates heat, you melt the thermoplastic, it cools down, and there you have a very good joint. And it's used a lot in the automotive industry, but mainly for unreinforced materials. Once you start putting fibers in and rubbing these materials together, the fibers will bang together, and on an individual scale, they're quite brittle and flimsy, so they end up looking a bit of a mess. So it's difficult to achieve good properties, but through some of our core research program projects funded by the members, we've managed to find a way of improving the strength and reducing the damage for linear friction welded thermoplastic composites. And now we're even applying the same technique to friction welding thermoset composites, which is interesting. Dissimilar materials. Well, as we all appreciate these days, as structures become more and more optimized, we end up putting the right material in the right place. So ultimately, we end up with structures that have a lot of different materials. And ultimately, these will all have to be joined together, which is very good news for TWI because we specialize in joining all materials and dissimilar materials as well. So we've developed techniques for joining thermosets to thermoplastics, thermosets and thermoplastics to ceramics. But one of the most interesting, I think, combinations of materials, certainly the one that our members are coming to us mostly for, is metals and composites. It seems that the properties of composites tend to supplement the deficiencies of metals and vice versa. So metals and composites work well nicely together. So over the years, going back to the early 2000s, even before that for the PCM technology, we've been looking at ways of improving the performance of a joint between a composite and a metal. And what you can see behind me is an example of surface sculpt, which is the metal surface treatment used in co-meld. So that little metal cylinder that the hand is holding, that's a surface sculpted metal. So it's a bit like, think of it like additive manufacturing, but rather than additive, it's displacive manufacturing. So we're locally moving bits of metal around on the surface to produce 3D features, which then grip into a composite to provide an integral mechanical locking or integral mechanical attachment that then enhances the adhesive bond between the metal and the composite, giving us a stronger joint. Some of the materials. Okay, this is an example here of a slightly unusual application. We know that the fibers in the composite carry the load, and so we're often very careful to maintain the fiber length and to put them where we want to. And then we join by mechanical fastening, where we drill a big hole in the composite, cut the fibers, and suffer the consequences, which can mean an inefficient joint with additional weight. So what we've looked at doing at TWI, starting about 8 to 10 years ago now, is making holes in composites without cutting fibers using a displacement technique. So this is mainly suitable for thermoplastic composites, where we can heat the thermoplastic matrix and then displace the fibers to the side to make a hole before cooling down the matrix, and ending up with something that looks very much like a toe steered or a toe sheared feature. But this can be made at any time after the part has been manufactured. And it can also be used to recover a hole if it's made in the wrong place or it needs to be repaired or removed. Then the elastic strain energy in these fibers, if we reheat it again, then they will return to their original position. And with the addition of a little bit of extra polymer, we can fill the hole in and you'd never know it was there in the first place. How many more have we got, Jasmine?
That's the last one.
This is the last one. Okay. I mentioned before a lot of activity in joining dissimilar materials, and this is where it starts to spread out away from our section into exploiting technologies in other parts of TWI. So we do a lot of work with lasers at TWI, laser scabbling for cleaning of radioactive concrete for the nuclear industry, but also laser cutting and laser drilling and laser processing of metals. So here's an example of a laser rivet technology that we developed. You can think of it almost like an additive manufacturing. So we put a composite and a metal together, and then using laser, we melt a filler material to produce a laser melted rivet inside the joint. The advantage is that the rivet is built on top of the metal and then overflows around the top of the composite without having to put a hole through both components. So we only get the witness marks of the rivet on the composite side. So the other side of the metal is completely free, aerodynamically clean, and visually beautiful. So is that the last one?
That's the last one. Yep.
Okay.
And in composite modeling side, we do have a different team working on it, but we do closely work with them. It could be on the process, for example, in the microwave heating. It's a very specific way of heating, so understanding of the power required in order to get the specific heat is very different to what you do in an oven or in a hot press or in an autoclave. So the simulation plays a big role in it. So we do the process simulation. And then when it comes to performance, also we do assess the performance of different parts or joints. I think another example other than what's shown here is, that's a process one for the thermal assisted piercing. We do the processing as well. Another example, I think I would say we haven't shown here is the electromagnetic signal transmission through composite. We can do that simulation as well. And then I will leave the functional composite for last, but first in terms of NDT and structural health monitoring, we do NDT of large complex structures in an automated system. I believe only TWI can do this work to this extent. So we do work with very large organization. We did work very large organization in order to develop this system. And then we have the full matrix capture, where you can identify quite a lot of in-depth details of a composite, either a damage or a void in the structure. And then most of you might be familiar with X-ray CT, where you can actually understand the damage, or again, during manufacturing or during the use of it, you can identify at a very high resolution. And also in 3D, you can see what's happening in the composite. We do have multiple systems, including the micro system. This says only 15 micron. Actually, the higher resolution system can go even smaller. Then in terms of structural health monitoring, we do use different technologies: acoustic emission, guided wave, different type of wave systems we use in order to assess the health of the structure as it's been used. And this is a case study we did. This is if I remember correctly, it's a 40-meter long blade. It's not a video, it's a picture. Blade where the acoustic emission sensors are embedded inside the blade, and it has been assessed to identify the crack as it initiates. This, just to clarify, this facility is not at TWI, but we can facilitate the structural health monitoring study, and then also the implementation in real life. Mechanical testing, if I remember correctly, I think we can now go to over 2,500 kilonewton.
I think we're up to about 3.5 meganewtons now.
Yeah, I think, yeah. And also we have the high rate testing. What's the is it 20 meters per second?
It's 20, it's an Instron VHS 160, so it's 20 meters per second in tension and 10 meters per second in compression.
The lab itself is UCAS accredited. We do have more or less all the required fixtures in order to do composite testing. Having said that, then the main advantage of TWI's testing facilities, it's a very large testing facility, and we can provide the required bespoke testing of either complex geometries or a test that has not been done before.
We have sorry, just Jasmine, just one more thing there. We have 2 digital image correlation systems. One is the standard system, which we use for the quasi-static testing, but we also have a high rate system, which will operate up to, depending on the windowing of the image, up to about 200,000 frames per second.
Yeah. And then I mentioned about the permeation testing facility we have, and we have great experts in this area who has been working in understanding the behavior of composite in relation to permeation. So this facility at the moment is heavily used for oil and gas industries. However, now it has been also extended to be used for hydrogen storage tank permeation measurements as well. The last one is the failure investigation. We do failure investigation. In this sense, of course, I'm showing about the most probably composite and polymers, but actually TWI does cover all variety of materials. It could be metal, it could be ceramics, and they are covered in different areas of the business. And in general, in order to identify them, either we might be using thermal characterization methods or NDT, or even mechanical testing, depending on the requirement. Again, a failure investigation is one of those, a bit similar to NDT. It relies a lot on the experience of the people. So we do have the staff who has many years of experience in order to be able to interpret the data to say why the failure happened. So it's not just about doing the testing, but also it's the major part of TWI is the consultancy on interpreting the data. It's the same thing. The last one is the functional composites. And first I'll go to the coating side. We have the functional coating, which is mainly focusing on hydrophobic coating, either for anti-icing or anti-fouling. This has been investigated for wind turbine, for aircrafts, and also for ships for anti-fouling. This has been developed and tested at TWI. And then the hard coating is, this is an example of thermally sprayed composite. And this is what you can see here is the carbon fiber composite with aluminum coating. You can either fully coat the surface, or you can put different patterns. We have the automated system for it. But special is the way the TWI has developed the method in order to spray this without damaging the fibers. That's the main expertise of TWI. And another advantage is this can be used for different things. But you can also use it in a composite as a primer, for example, where the pull-off load is about 12 megapascal. So it's quite high. Apparently, a standard primer or paint is about 4 megapascal. So the pull-off strength is very high. So what people at the moment using is for lightning strike protection, and also for where the patterns are, we can also use it for different type of materials. For example, we can put a copper and get a conductive structure. I can't remember how small we can go. Do you remember, Chris, how small we can go?
How thin or how small a feature?
How thin?
Thin is probably about 50 microns.
Yeah, I think so. So you can put different patterns. It's used for a variety of reasons. It's used also for radar, for metamaterials, so different functions you are using it. And the materials we have put is we have put aluminium, copper, Inva as well. There are a number of materials you can put, but I mean, I don't have the example here, but you can put if you want to put a metal coating on a composite and you want to get a thick layer, you can do that as well. The last one I have is a SurFlow. That's a technology developed at TWI, and it actually won in 2018 the Composites UK Industry Award for Composite Design, where we can send signal through a composite structure. I'll quickly put this video. The aim is to make the composite multifunctional. So what happens is we do transmit a signal from left to right. In order for this technology to work, you need a conduct layer on one side, and the other side has to have a dielectric layer. The conductive layer doesn't actually carry the signal, but it prevents the signal from escaping the other surface. So the signal propagates from left to right. The advantage is because it's electromagnetic waveform. As long as there is a continuous path, the signal will find a way, even if there is an obstruction or if there is a damage. So unlike a cable, where if the cable is broken, you would lose the signal. Here, as long as there is a continuous path, you still will receive the signal. However, what happens is when the signal gets interrupted by a damage or some sort of an obstruction, there is certain change into the signal signature. So you can actually use this method to also either as structural health monitoring or NDT. And you potentially could also triangulate and position where the damage is. Similarly, even if an object is in a certain proximity, that can also be identified by the change in the signal signature. Where it can be used anywhere where there is a composite and where there is a need for data transmission. there's quite a lot of information regarding this. If you're interested, you can ask afterwards. There's quite relationship to different frequencies, how it would behave when there's a joint, and how can we use it as a proximity sensor or damage detection. A lot depends on the frequency we want to use. One of the main advantage, other than you get the signal, even the composite structure is damaged, is that the speed is about 3 gigabits per second per channel. So it's about 3 times faster than 5E Cat Ethernet cable. So it's very fast. It's better than Wi-Fi. In Wi-Fi also the issue is that the reliability of signal might be low, and the signal may be interrupted by external sources. This method is a lot more secure. However, it's still fairly low TRL level method. There are a number of, I haven't shown here, they are available, and if you're interested, I can send you the links. There are a number of demonstrators on YouTube where we send signals, either video signal or control signals through the composite. So one way I explain this is it's similar to Wi-Fi, but the difference is the signal propagates not through air, it propagates through the composite structure. The signal is bound to the composite structure. I already said that one anyway. So I try to keep it as low as possible, but still I took 35 minutes. So I think now we could move on to the Q&A. We'll try to answer as much as possible. As I mentioned, different areas are covered by different areas of TWI. If you have further questions that we won't be able to answer, we can pass you to the relevant experts.
That was brilliant. Thank you very much for that. I've certainly learned an awful lot about what you guys do, which is fantastic. And that was fantastic. So does anyone have any questions for Jasmine and Chris?
Hi, it's Mark here, PPG. Just it's not a technical question really. It's just really if you kindly if we can follow up afterwards, I'd be quite interested in some of the SurFlow technology talked about, and maybe some of the coatings as well. If we could just have an offline chat, I'd be interested to have a discussion.
Yeah, definitely.
Yeah, that'd be great. We're working PPG as a company, although it's known as a coatings company. We're doing a lot of polymer and work composites globally across a range of industries, and we're interacting more and more within our traditional customers who have used metal, if you like, or magnesium aluminiums, and now they're moving into composites. And there's a lot of crossover in technologies. Some things we've been developing, some things you guys have been doing. So I'm beginning to just sense a number of things. So I think some of our scientists would maybe be interested in chatting to you. And I'm not a scientist, so don't ask me any questions. But a lot of my role is to identify technologies within PPG. We're discovering within PPG that we've got more stuff than we think we have. Most of the time, none of us know what the other part of PPG is doing. So I'm quite interested to see, because of my work with composites in the last few years, with a number of different clients and some of the innovations that our clients are working on. And it may be a combination of some of the things you're working on and what we're doing. So I'd be quite interested to follow up with another call, please. Yeah,
sounds good. I think I can get the contact from Charlotte anyway. And then
that's fine. Obviously, if you want us, we can sign in. DAs, that's fine. Okay. Thank you.
Hi.
Hi, Rizwan.
Right. So I think it was a very interesting talk. There were a few things which have got my interest in, especially we have been working recently with one of the thermoplastic resin systems called as Helium. It's a MMA-based resin system, which can be used with the standard resin infusion process. So because of its greater recyclability, we see that as a potential candidate that can replace epoxies in many systems. So in last few years, we have done a lot of characterization work in terms of the impact damage as well as compression after impact damage, and also developed some models related to 3D composite reinforced with helium resin. And going through your talk, one thing which I can see potentially, has some scope of work. And if you have done some similar work, you can, you can elucidate that, whether you have worked with helium resins in terms of the joining processes, because that's a newer resin system. So I'm interested to know if you have done any of those welding-like joining processes with helium. And if not, will you be interested to take that work further?
I'll pass it to Chris.
I was just going to say, do you want me to take this?
Yeah.
Well, to be honest, we haven't done any ourselves at TWI. It is a material I'm familiar with, mainly because we were involved in a Horizon 2020 project called Fibership, which I think ran from 2018 to about 2020, might have been 2017. A very large collaborative project. I think there were 15 members in the consortium. It was Spanish-led. And that was all about trying to increase the amount of composites in large-scale ships. So these are ships that are more than 50 meters long, so container ships and naval research vessels and fishing vessels. And at the beginning of the project, there was a material selection exercise that was carried out by one of the partners, which is University of Limerick. And helium was one of the materials selected as a potential for investigation in the project because of its good properties, suitability. Unfortunately, we didn't carry that one through in the project, mainly because of the short deadlines, the timescales in the project, and the lack of availability of the resin system at that time. It was deemed that it wouldn't be suitable for the large volumes that will be required for large-scale ships in the next 5 years. So we're reverted to more traditional epoxies and vinyl esters for that project. But it is a very interesting material, and I'm interested to get my hands on some and play around with any of the welding processes that we have.
Okay, that will be, I think, interesting. So at the moment, like I said previously, we have done compression after impact and impact testing with 3D composites. But right now with Dr. Tahir Sharif, who's also attending this webinar with us. So we have got some 3D tufted samples as well that we are looking for fatigue tolerance, damage tolerance as well. And we are thinking of actually using helium there as one of the resins as well. And we'll be very interested in looking at comparative properties of a cured tough lap joint versus a 3D tufted lap joint, for example, with helium. And if we can find some industrial partners or some industry case study where they can be, that I think can improve the impact of our work. So rather than being a purely academic work, which it is at the moment, we would like to see if we can actually have some sort of an impact case study. And the other thing which I was very interested in was that needle piercing that you mentioned there. And I was surprised that you're saying that there's no fiber breakage in that process, because I would imagine that, at the point of the piercing, there will be some disruption, or do you, I don't know how that works. So is it because of the thermal input that it becomes so softened that, it's just easy? So yeah, can you please just slightly explain that?
Yeah, sure. You do raise a good point, actually, and I wasn't strictly true. I mean, no fibers were harmed in the making of this whole. There will always be a little bit of damage, but if you're talking, a handful of fibers in several million, it's effectively insignificant. It can be a difficult process to control, because when you plunge your pin or your profiling tool into the composite, there is always a downward component of the thrust. So we're never just moving the fibers sideways. There's always a bit of downwards, and so there will be a tendency to fibers move slightly down, and we see this in some of the micrographs of cross sections. It's very difficult to get a perfect interference clearance fit at the exit of the hole as well, so you do get a little bit of fiber for going down the side there. But on the whole, the fiber damage is very small, because we notice no difference in the open hole tensile strength of a composite with this compared to that with a drilled hole. We're looking at other properties as well, open hole compression and shear, but it does maintain the integrity of a lot of the fibers, and you can see this from X-ray CT data afterwards. You can see the fibers that are curved around. Obviously, it depends on how far you push these fibers relative to the area that's heated. So there's a ratio of heated area to hole diameter. Because if you make the heated area smaller and smaller, and you make the hole bigger and bigger, the fibers that are being deformed become restrained over a shorter and shorter distance, so the strain increases. So at some point you're going to break them because you're stretching them so much. So the bigger the hole, the bigger the area that you need to heat.
Probably it will then work better with the fibers which are more, which has longer strain to failure.
Exactly, it works better with those fibers, and it also works better with smaller holes, which is why after that project we moved over to a follow-on project with a Eng doc at Surrey University, looking at perforating composites, so producing a large number of small diameter holes for fluid flow for leading edge de-icing, or for pressure wave dissipation for blast protection systems, or noise reduction for aircraft landing gear. So the smaller the hole, the smaller the residual strain in the fiber, so the better the composite. But it's a different process then.
Thank you. I would like just one more question, and then I'll like the other participants to all to ask questions. Don't want to hijack the whole meeting. So in terms of the multifunctional composites, one thing that we are actively trying to look at, and also trying to find some partners, and if anybody is interested here, is the concept of the structural batteries. So have you done any work in terms of the multifunctional structures in that area at all?
We are doing some work. Well, one of the material is the SurFlow one, but we also work in terms of the battery side. At the moment, we don't have any single client type projects, but we do have a PhD student looking at the thermal improvement of the thermal conductivity for battery casing.
Right. Okay.
Not for structural batteries though. The closest we got to there was about 15 years ago. We developed a composite sandwich structure where the core of the sandwich structure was a series of fuel cells. So it's a fuel cell integrated power supply inside a composite structure.
Right.
We had some initiative to work with, but the project didn't go ahead because of the Innovate UK funding. It didn't go through, but to use graphene and have composites for that was actually what we were trying to do, was to combine graphene and the batteries with composite for SurFlow for self-powered sensing.
Right. Okay.
Because in the SurFlow technology I mentioned, we can send signals, but we can't send sufficient power. So you need power source. So we were looking into developing composite battery cells with graphene.
Okay. Yeah, because in recent years, I think the technology has moved on in terms of the structural batteries, and we are getting now a good power density, around 175 or between 175 and 200, which is a reasonable power density, I would say. So I think that's again an area where we would like to see if maybe after the meeting we can have some follow-on discussion and see if we can find some project partners that can be interested in that sort of a work. So
yeah, definitely. Yeah.
Okay. Yeah, thank you so much. Thank you.
Anyone else?
I'd be interested, Jasmine, just knowing what the typical membership fees are for TWI. What's, obviously I imagine there's a range depending on size of company, but
Yeah.
What's your typical sort of membership fee that you charge?
I had to be honest, I could not give a number. I don't know whether Chris can. I doubt he can. As you mentioned, it depends on the number of employees. We have a different team dealing with the membership.
Yeah, it's for the smallest companies, it's generally about £4,000 for an annual membership, all the way up to, if you're a multinational company, let's say Shell, which has facilities in lots of different countries, all using our resources, it might be as much as 70, 80, 90,000 for a year's membership. Right. But what's important is that both those organizations will get the same benefits, whether it's 4,000 or 90,000. The only advantage, the only reason for the larger fee for the larger organization is generally we get a lot more inquiries through the larger organizations. Yeah. So on a pro rata basis, they're effectively paying more, but they get access to all the same facilities, all the same features, all the same benefits as the one-man band member.
Yeah. And similar to Composites UK, you can also, because the large organization, maybe only one area is working on composite or one technology. So you could have membership for only that part as well.
Okay. No, I was just interested to know what was the typical sort of range.
So you'd be happy to work on single projects as well, where you just use in specific use.
What do you mean?
So if you just had a single project in, say, Europe instead of the States or anywhere else, you could work on a single project, a single item, or does membership get you access across what you're doing? Maybe it's a conversation to have with your membership team. But
yeah, if you were a large organization and there was just one small part of your company that was interested in one specific project that was only relevant to that part of the company, we could arrange for a local membership of that organization. So you wouldn't have to join as an international corporation. You join as a regional, just for that project.
But you cannot just do one. You cannot do a project without having any membership. If that.
Of course, no, membership is priority now. I get
it. Will be an annual membership fee.
Yeah,
no problem. Yeah, that's fine.
And one of the advantages of the membership is that, as Jasmine mentioned at the beginning, it gives you access not only to the current core research program projects that are being carried out, but it gives you access to every single core research program project we have carried out in the past. So you can dive into 30, 40, 50 years of research reports and harvest all the knowledge from it. You don't own any of that knowledge, but you can see what we've been doing and see where you can possibly exploit that yourselves.
Oh, that sounds interesting. Thank you.
But also, for example, I think Chris knows about this actually a lot better than me. Also, if it's something, if you have a question, we would do over the phone consultancy. Is it up to 2 hours, Chris?
Yeah, as part of our standard membership, we allow generally a couple of hours a week free telephone consultancy. And this is one of the benefits of membership, which is least used. I don't think we've ever had to contact a member and say, just back off a little bit, you're using us too much. Usually it's the other way around. So there's one company who's a member at the moment that I'm helping, and we're not doing any project work with them, but probably 1 hour every week or every couple of weeks, we get together and have a chat, and they tell me what they've been doing and what progress, and I sort of listen and advise them and steer them. And that's the way that works, which might not seem very profitable, but other parts of TWI are getting 50, £100,000 projects of this company, because that's where they can get the benefit from our membership. So I'm helping them. That's
actually very valuable.
Basis.
Yeah, that's very valuable. Actually, much more valuable than people think. There's a lot of interaction on individual levels with scientists that come up and confirm some of their ideas and things they're working on. So,
sometimes it's just as simple as, can you advise me whether this test method will be suitable? And I've got instant online access to all the standards, and I can quickly have a look if it's one they're not familiar with, and just go through it with them and say, you've got to make sure this and that, and ultimately advise them. It's all part of their membership. They don't have to pay extra for it.
Are there any more questions for Jasmine and Chris? Okay, are there any questions for Composites UK, or is there anything that you would like to raise?
Just one thing which I would like to ask is, if we want to follow on from this meeting, Chris and Jasmine, how can we contact you? Will you be sharing your contact information, or?
I can drop my email on the chat.
Yeah,
Sure.
thank
If not, you can always get hold of us through Composites UK as we're a member.
Yeah.
Yeah, we're happy to pass on any inquiries, guys.
All right, thank you very much.